Hello and welcome to the online training course on temperature measurements during ultrasound applications. This course is provided in the framework of the project RaCHy, Radiotherapy coupled with hyperthermia, funded by the MPIR program, co-financed by the participating states and from the European Union Horizon 2020 Research and Innovation Program. This is the first lesson of the training course. My name is Piero Miloro from the National Physical Laboratory in the United Kingdom. This introductory lesson will introduce the topic of temperature increase under ultrasound and discuss why we need measurements to quantify this temperature increase. First of all, what is ultrasound? Ultrasound is a mechanical vibration that propagates through a medium as a pressure wave. The wave is defined by its frequency, intensity, speed, and direction. By definition, ultrasound is a sound wave with frequency higher than the human hearing limit, that is 20 kHz. Medical applications are usually in the range of the megahertz, which is 1 million of oscillations per second. When an ultrasound wave travels through a medium, it loses part of its energy through attenuation. The main factors contributing to attenuation are scattering, which is due to inhomogeneity in the path of the ultrasound wave, and can have different forms depending on the size of the inhomogeneity compared to the wavelength. The second factor is absorption, which is the conversion from organized vibration, which is ultrasound, to random motion, which is heat. In tissues, the largest contribution comes from absorption. The mechanisms for absorption include friction due to fluid viscosity, molecular relaxation, and damping losses. Absorption varies locally and depends on tissue heating capacity and conductivity, on the perfusion, which is the quantity of blood in that specific part of the tissue, and on the properties of the ultrasound wave, in particular frequency, intensity, and duration. Absorption causes the temperature to increase. The equation for the variation of temperature with time is reported in these slides, and it depends on diffusion, on the heat source, and on perfusion. The heat source in this case is the ultrasound itself, and the easiest simplification correlates it to the absorption coefficient in tissue multiplied by the intensity. The measurement of absorption coefficient is extremely complicated, so in most cases the attenuation coefficient is reported. Attenuation usually comes in form of a constant multiplied by the frequency elevated to the power b, with b usually between 1 and 2. Different tissues have different attenuation, with liquids attenuating less and solids attenuating more. So blood has a low attenuation coefficient and bone have high attenuation coefficient. In the middle there is fat, liver, muscles, and soft tissues in general. Temperature increase always happens when tissues are exposed to ultrasound. Sometimes it is a side effect that must be limited. Sometimes it is desired. It must be limited when it's used for diagnostic or monitoring purposes. For example, it is easy to imagine that obstetrics applications need to limit the temperature increase to a minimum to avoid potential damage to the fetus. Increasing risk factors are in fact the presence of sensitive tissues, the presence of bones in the path of the ultrasound beam, air gaps because they provide a perfect reflection, or the use of endocavitary devices because they are closer to the target and because in the body there is less opportunity to dissipate heat that is generated at the surface of the probe. Sometimes, on the other hand, temperature increase is desired, for example for therapeutic purposes. Hyperthermia is a therapeutic protocol where there is a protracted mild heating at temperatures usually between 40 and 45 degrees Celsius for up to 60 minutes. Hyperthermia increases the blood flow in the target, is known to be a chemosensitizer and a radiosensitizer, and the effects are typically reversible. If the temperature increases are higher, these are called ablation therapies. These usually involve rapid heating above 60 degrees Celsius that cause coagulative necrosis and cell death. Temperature increase always happens in tissues, and there are many reasons for which we want to quantify it. It can be to increase the confidence on the safety of the procedure, it can be for the introduction of new technologies in diagnosis or therapy, or it can be so that the therapeutic thermal applications can be quantified. In particular, it is important to know that the right amount of heat is delivered to the right place, and that the surrounding tissues are not affected by undesired temperature increases. Finally, quantification of temperature increase improves the repeatability and enables multi-center trials of thermal therapies to be compared. Thank you for the attention.